At negative 2 comma 0, what we have to do is plug in the corresponding values where it corresponds in the equation. So y prime equals negative 2 squared plus 0 squared minus 1, which is 3. That means the slope is 3. And of course we can do this for other points. How about the point negative 1 comma 0? Well, negative 1 squared plus 0 squared, that's 1 squared minus 1, that's equals to 0. And we can keep filling in some of the other points. How about the origin 0, 0? Well, that's 0 squared plus 0 squared, which is 0 minus 1, that's negative 1. And I'm going to fill in the table the same way the book has it. So instead of doing all these calculations, I will just give you the answers to this calculation. So that's a 1, 0, 0. And 203 and negative 1 0 0 negative 1 1 0 1 0. And you can verify all these calculations. Just plug in the corresponding value of x and the corresponding value of y, and this is what you should obtain for the value of the slope. 1 1 1 2 1 4. All right, so number 1, let's sketch the solution curve that passes through the origin. That is, we need to look for the order pair that contains the origin in this case. So that is going to be this point right here. All right, so we need to go to the origin in this case and verify that indeed the slope is negative 1. So let's check. Go to the origin. And does that little line contain a slope equal to negative 1? Alright, so that means, well, according to our calculations, this is consistent. So all we have to do is trace the solution graph that passes through that point. In this case, I'm going to do this pretty much. But of course, we have the actual solution right next to it, just so we can verify our calculation. Now, of course, we can have many different solutions to this differential equation, and well, that's on the very last. I mean, at the very bottom of the page, we have many different solutions. So notice, check this out. For example, notice, for example, at negative 1/2. Notice at negative 1/2 how we have different situations. We have a situation in which the slope is negative, the slope is almost 0, and the slope is positive. So these phase diagrams, or these direction fields, provide us with a good picture of the different solutions with different conditions that the equation may have based on, in some cases based on our needs. So for example, if we wanted to define, or rather to design an experiment in which we need a decay, well, so then we would need to have an initial condition for a differential equation so that at this particular value, this models decay. If we want to model something that remains constant, well, maybe we need a different condition, or if we need, something increasing. For example, if you are modeling a profit function, for example, well, you want to make money, you don't want to lose money, so you want to make sure to manipulate a differential equation so that the initial condition yields an increasing function, that is an increasing profit, not a decreasing profit. Of course, you can study these values to make sure what not to do on your profit function, for example, so that doesn't mean a loss, right? So, and that's different phenomenon that can occur at the exact same value of x. So that's why it's another importance of keeping these diagrams in mind, because they help us predict what can happen at different values of x depending on the initial conditions. So this concludes this section, and the next section is section 9.3, separable equations. So, well, we already did a little bit of solving differential equations using the method of separation of variables. However, However, we didn't formalize the method. All we did is just what I just told you is have all the y's on the left hand side and all the x's on the right hand side, and that was it. I didn't tell you what's the formal definition of separating the variables. So separating the variables, so we consider a differential equation that looks like this. It's a first order differential equation because the highest derivative that we will see in this equation is the first derivative. So if the equation is of the form dy dx equals f of x over g of x, then we can separate the variables because we can multiply both sides by dx and we can multiply both sides by dy, giving us g of y dy equals f of x dx, and we just separated the variables, and then all we do is the reverse of finding the differential, which is to integrate, which is really this process we have over here. All right, so finally we got a formalization of what this separation of variables is. All right, so let's go ahead and solve and go and look at an example. So let's solve the differential equation dy dx equals x squared over y squared, and then we find the solution of this equation that satisfies the initial condition y of 0 equals to 2. So number one, okay, let's go ahead and rewrite the equation dy dx equals to x squared over y squared. Okay, so in this case the equation is separable. We can move the y squared to the right, to the left hand side, and the dx to the right hand side. So y squared equals to y squared dy equals x squared dx. And now that we have the variables separated, we may go ahead and do the integration. All right. Oh, come on. So, well, the integral of y squared is going to be y cubed over 3 equals x cubed over 3 plus c. Alright, so someone in the class asked about, I don't know if it was this class or my other class, why do we just add the plus c to the right hand side of the equation? In fact, that's the only one side we do. I mean, if essentially, okay, let me do something on the side real quick. So if we do y cubed over 3, and let's call it plus c1, x cubed over 3 plus c2. Okay, so essentially that's what we have to do. Add one constant on the left hand side for the corresponding integration and add another value of c to the right hand side for its corresponding integration. However, when we try to solve for the differential, for the y value, for the dependent variable, when we subtract c1, well, we can subtract them here, and y cubed over 3 equals x cubed over 3 plus c2 minus c1. But notice I didn't leave this as a c2 minus c1. And well, the thing here is when we subtract these constants we don't know what they are. Those constants are to be determined by the initial condition in this case. So this is what happens here. Here we combine c2 minus c1 and we call it c. And in this case by a process called absorption. So in this case when we combine two unknown or two arbitrary constants or more, whether by subtracting, adding them, multiplying, whatever operation you do with them, this is called absorption. It's called absorption in this case. So ultimately, when we solve a differential equation by this method of separation of variables, all we do is add the plus c only on the right hand side of the equation. So we're almost there to get the general solution. So we can multiply this equation on both sides by 3, and well, So that's going to be y cubed equals x cubed. And you might be thinking, oh, we also distribute the 3 with the c. Well, technically we multiply the c times 3, but that's just another arbitrary constant. Times 3, that's just going to be another constant, and again by the same process of absorption. So we only do the operations with the variable terms or constant terms, but for this arbitrary constant c, we just go about the absorption and we just keep writing the plus c. In some other cases, it's going to work a little differently. You'll see as we move on through the different examples. So in this case, we can solve for y by taking the cube root of, on both sides, x cubed plus c. So in this case, this is our general solution. Now they're asking us to find the particular solution. Again, whenever we solve a differential equations, we are essentially finding the picture of a family of functions. Well, if we're interested in a particular member of this family of functions, we need to be given a condition. Well, so we're looking for the family member of these functions that contains the point 0, 2. Recall that this notation here, y of 0 equals to 2, means when x equals to 0, y equals to 2. So let's see. So with y of 0 equals to 2, all we do is plug in the values where it corresponds. So y equals to 2 cube root of 0 cubed plus c. And well, so that's going to be 2 equals to the cube root of 0 plus c, which is just c, cube both sides. That's going to give us a c equals to 8. Once we find this this value of the constant of integration, we may go about writing the particular solution, which in this case is y equals the cube root of x squared, I mean x cubed plus c, not plus c, actually plus 8. And this will be our particular solution. Alright? Pretty much the same idea that we discussed last time about how we solve this kind of equation. But last time we were, well, last week actually, we were working with solving y equals to x, because that one was an easy one to solve before we actually define this method formally. Alright, let's go about another example. For the next example, solve the differential equations dy dx equals 6x squared divided by 2y cosine plus cosine y. Well, in this case, they're not asking us for a particular solution, just a general solution. And we know that because we're only given the equation. They're not giving us any initial condition in here. Alright, so, and in this case, let's see if we can separate the variables here, because in some cases, it may not be the case. So let's multiply, let's cross multiply. So that's going to be dy, 2y plus cosine of y dy equals 6x squared dx. So in this case, it's possible to separate the variables. Alright, so let's integrate both sides, and we can integrate to y. That's going to be y squared, and the integral of cosine, which is sine y. Again, we don't add a plus c on the left hand side, we only add 1 on the right hand side. So the integral of 6x cubed, 6x squared, that's going to be 6x cubed over 3 plus c. Right. So in this case, we can reduce 6 over 3 to leave us with 2x cubed plus c, and everything else on the left hand side the way it is. And in this case, we can leave the solution in this form, because unlike the previous example, we were able to solve the equation and get an explicit function of x, in this case that is y as a function of x. However, in this case right here, y squared plus sine y, try to solve for y, it's simply not possible to get this done. Alright, so unless, I mean, what can we do about it? You know, something like maybe solve for sine equals to x cubed minus y squared plus c, and then take the arc sine. However, notice in this case, it's still not an explicit function of y, because we have y's on both sides of the equation. So no, we can't solve this equation. So this would be a good answer over here. Alright, let's see what's next. So find the general solution for the differential equation y prime equals e to the x plus y. Notice the notation this time. In this case, we're not given the Leibniz notation, which clearly shows the quotient between between the change in the x direction and the y direction. In this case, we're given the prime symbol. So number one, what we have to do is change the derivative symbol to that of the y dx equals e to the x plus y. Alright, however, in this case, notice the right hand side, we have only one single term, e to the x plus y. So because we only have one term and that term contains both the x and the y, well, we cannot separate the variables just yet. So we need to do some algebra first, like using the laws of exponents. Recall that e to the x plus y, any base raised to the sum of terms, is the same as e to the x times e to the y. So that's basic laws of exponents from algebra, and then only then we would be able to solve or to separate the variables. So let's see, so we can multiply both sides by dx first. I'm going to do one step at a time. dy equals e to the x, e to the y, dx, and then divide both sides by e to the y. That's going to be dy over e to the y equals e to the x dx. And well, we got the variable separated in this case. However, the one on the right hand side, it's pretty straightforward to simplify. No problem, no issues with that one. However, the one on the left hand side, we have the exponential in the denominator. We need to have it in the numerator so we can integrate this one. So that'll be e to the negative y. All right, and we're good to go. We may go about the integration. Okay, so the right hand side, the integral of e to the x is simply e to the x plus c. On the left hand side, the integral of the exponential is also itself e to the negative y. But in this case, we don't add the plus c. However, this one goes negative because of the coefficient of the exponent. In this case, is negative. So in this case, we need to go about solving for y. And in this case, it will be possible to get an explicit solution. That is, a solution of the form y equals some function of x. So number one, I'm going to multiply or divide by -1 on both sides of the equation. All right, but be careful. Not everything gets multiplied by -1. So number one, so that's e to the negative y equals -1 times e to the x, that's negative e to the x, and c times the -1. Recall that by absorption, an arbitrary constant multiplied by whatever number, whether this is positive or negative, it's always c. It remains c by absorption. So, well, we are a couple of steps away to get this equation solved. So we can get rid of the exponential by doing the inverse of the exponential, which in this case is to take ln on both sides. This will cancel the ln with the exponential, and we're left with negative y, and that's equal to ln of c minus e to the x. And we'll just divide both sides by -1 to get y equal to negative ln of c minus e to the x. And that's our general solution. Again, it's a separation of variables. This time we're required to use some laws of exponents before we get the separation done. The rest of the problem, it's the same rules of integration and the same techniques to solve equation by doing inverse processes of what we are obtaining as we go every step. All right. Let's see. Let's go about the next one. Yeah. Okay, so for the next one, solve the differential equation y prime equals x squared y. All right. Yeah, so this one is the one that's going to have a few more details. So, number one, let's change the sign of the derivative, dy dx, x squared y, and then let's separate the variables. So I'm going to multiply both sides by dx. That's going to be dy equals to x squared y dx, and divide both sides by y. So the variables are separated in this case. And we may go about the integration. So let's integrate both sides. And the integral of dy over y, that's ln of absolute value of y. Don't forget the absolute value bars. In this question in particular, in this situation, these bars are going to be very meaningful. X cubed over 3 plus c. So we're essentially done solving the differential equation. We may go about solving this for y. So number one, we need to get rid of ln, and we also need to get rid of the absolute value. So there's a couple of things that we need to get rid of first. So number one, let's go about eliminating the natural log. Notice how these two cancel, because those are inverses of one another. And that's going to leave us with the following, that is absolute value of y equals e to the x cubed over 3 plus c. All right, I'm gonna look at the absolute value bar after I'm done with simplifying the exponential on the right hand side. So again, in this case, we're going to use that law of exponents when we have e to the a plus b. I'm going to use it backwards, not the way we used it before. So this will be y, the absolute value of y, e to the x cubed over 3 times e to the c. Just the same way in general, whenever we have e to the a plus b, this is the same as e to the a times e to the b. When we have the same base, what we do with the exponents, when they're multiplying, we add them, or vice versa. When we have only one base, we have an addition, we multiply the two exponentials. Alright? But now, check this out. Over here, this e to the c, whoops. This e to the c, it's just going to be another c. And this by absorption. Alright? This will go by absorption, so e to the c just becomes a c. Well, let me continue up here. So that's absolute value of y equal to c e to the x cubed over 3. Alright? So now we need to get rid of the absolute value bar. So number one, okay, let's go back to basic algebra and see how we solve absolute value equations. For example, absolute value of x minus 3 equals to 2. Okay, how do we solve that equation? Does anybody remember how do we solve this absolute value equation? Plus or minus 2. So there's a couple of ways to represent this. Either you split it into two equations, x minus 3 equal to negative 2, or x minus 3 equals to positive 2. If you want the compact way to solve this equation, you might want to go x minus 3 equals to plus or minus 2. Alright? That's because, well, the definition of absolute value, in this case, this equation is asking us for the values of x that are 2 units away from 3. Well, if we look at those values, 0, 1, 2, 3, 4, 5, 6, 3, so we go to the number 2. What numbers are 3 units away? So on the right direction, so that's 2, 3, 4, 5. And 2 minus 3, that's a negative 1. Alright, if we solve the equation, in this case, or actually, wait a minute, no, it's positive 1, right? Is it? Yes, positive 1. But that's not, oh yes, and the center should be 3, right? Yes, 3, and then from here we go to units, 1, 2, that's 5, and 1, 2, that's 1. If we solve, x equals to 1 and x equals to 5. So that confirms the result, and that confirms the definition of the absolute value bar. So it doesn't matter if I move in the right or in the left direction, it's the same number of steps in this case. So we're going to go about this the same way with this exponential equation. So if we solve this absolute value, okay, we can get rid of the absolute value bars. However, put a plus or minus c e to the x cubed over 3. Now, what happens with plus or minus c? Because that's just a constant. That constant multiplied by 5. It's just a constant, right? That constant multiplied by negative 7 million. It's still just a constant, right? So in this case, we can get rid of the plus or minus because it's just a constant, and by absorption, and that's our general solution. And again, let me point it out, by absorption. Okay? So that's the only thing that might look a little weird when solving differential equations, this absorption thing. Everything else will just work the exact same way. Alright? So these are a few examples on how to solve differential equations. Yes?
Well, we have questions before. Can we skip over the plus or minus? Yes.
Well, just show the plus or minus, and then just like this mentioned, that by absorption, that becomes just C. For the next topic in this section, which actually it's a long one, it's to find families of orthogonal trajectories, and the last topic in this section is word problems applied to mixing solutions. All right. Orthogonal trajectory. So an orthogonal trajectory of a family of curves is a curve that intersects a curve, each curve for the family orthogonally, that is at right angles. Well, what's that word about orthogonal? Well, orthogonal is just a fancy word to say perpendicular. The thing is, well, when we talk about perpendicular lines, for example, in the simplest case, well, we know that these two lines form a 90-degree angle whenever they intersect, right? So but that's not the only situation in which we see the perpendicular. We can have a couple of planes being orthogonal. That's something you're going to look at later in your calculus 3 course. What else? So functions, then even though it's not because of the curvature of the circle here, yes, it forms a 90-degree angle here, but still, because of the curvature, it doesn't look like it's actually a 90-degree. But the thing here, we're looking at the slope. For example, at this point, the slope of the tangent line actually forms a 90-degree. Well, in this case, this is only a straight line. Well, if we find the derivative of a straight line, we're going to get the slope, and then we use that slope at any point. Well, we're going to get back to the same equation of the line. And in this case, I think it's easier to see the orthogonality, the perpendicularity, but rather we call it orthogonality this time. All right. So, well. In this case, well, what are we seeing in the picture? So here in this picture, we are seeing that a family of lines is orthogonal to a family of circles. Actually concentric circles, because they all share the same center, in this case the origin, if we were to describe them more properly. All right, well, so let's look at one example. They're asking us to find the orthogonal trajectories of the family of curves x equals to k y squared, where k is just an arbitrary constant, like the constant of integration, if you will. For now, we're going to call it like this. But later, when you get to calculus 3, that constant k is used to describe the different, in this case, level curves, and that's something that you might have seen before. These level curves, when you're looking at the news, for example, they tell us about the different temperatures across the United States. How is the temperature going to be at different places? And then you see some of these level curves and different colors for different sectors on the map. Actually, those lines, those level curves, are the set of all points in the United States where the temperature, in the case of the temperature, is exactly the same. When you move away from that curve, if you get to a darker color, well, that's going to be a higher temperature, or a clearer color, it's a lower temperature. Well, that's something you will discuss in a lot more detail when you get to calculus 3. Just to give you the picture of where is this used, that's why I'm just giving you this example. All right, so let's see. So this is what we have to do. Number one, we need to find the derivative for this function, and in fact we're going to use implicit differentiation, because if you try to solve for y, that's going to give us y, or rather y square root of k equals plus or minus x, and well, we don't want to have trouble with two different solutions, so we're going to do it in implicit form. So from implicit differentiation, the derivative of x is just 1. The derivative of y squared, that's going to be 2ky. But you might remember from implicit differentiation that every time you differentiate a y term, you multiply by dy dx. So this is what we have to do. We need to solve for dy as usual. Dy dx equals 1 over 2ky. However, in this case, this k needs to be replaced into its corresponding values of x and y. So we're going to use the original function, the given function, or equation rather, or implicit function. Well, it's technically not a function. Solve for k, and k equals to x over y squared. So this is what we're going to do. We're going to replace this quantity over here. So dy dx equals to 1 over 2 times y, and that quantity x over y squared. All right. And well, I'll explain in a second what are we doing here. So in the meantime, let's simplify. Y over y squared cancel 1 power of y, and that's going to leave us with dy dx equals to 1 over 2x over y. Now the thing here is dividing by a fraction, it's the same as multiplying by the reciprocal of this fraction, which in this case is dy dx equals to y over 2x. Well, what's this? Again, in general, what does the derivative give us? What information does the derivative give us? The slope. Well, so in this case, number one, do you recognize this form x equals ky squared? Does that remind you of some of the conic sections in particular? If so, which one? For example, if I give one value of k, for k equals 1, I would get the equation x equals 1 times y squared. What's the graph of this equation? We have actually it's a quadratic equation in 2 variables, so what does that represent? Well, what if I change the variables to make it easier? Y equals x squared. What's y equals x squared equal to? What is it? Loud, please, so I can hear. What is it? Parabola. Okay, it's a parabola. This one opens up, right? Okay, what would be this parabola looking like? Anyone? Not opening down? To the side, right? And this is what we have. Don't we have sideways parabolas here, the ones in blue? All right. Well, so this in this case represents the slopes of a family, the slopes of a family of parabolas of the form x equals ky squared. All right, so that's, now we want to find the orthogonal trajectory as well. Something we know about, for example, so if I have, for example, the slope or the tangent line for the parabola at this point. So that's going to be whatever slope is this, right? Recall that orthogonal in this case means perpendicular. So in this case, we would need to find the slope of the perpendicular line. Now, from the theory of linear equations or linear functions, if we know the slope of a line, how do we get the slope of the orthogonal or the perpendicular line? Does anybody remember that part? What is that? The inverse, and what else besides the inverse? And the opposite in sign. So that means, so in this case, the slope of a family, the slope of a family of orthogonal trajectories is given by, okay, the same slope dy dx, but in this case we need to find the reciprocal of this quantity, 2x, and 2x over y. and also change the sign, because recall that two lines are perpendicular if that condition is met. Number one, the two things must happen: the inverse or the reciprocal and opposite in sign of the original slope. And then from here we're going to go back and solve this differential equation to retrieve the original function that will describe the family of orthogonal trajectories. And well, we started with sideways parabolas. Hopefully, our expectation is that when we solve this equation, we get ellipses as our family of functions. So let's see if that's the case. So number one, separate the variables. Y dy equals negative 2x dx. Integrate both sides, so that's going to be y squared over 2 equals to negative x squared plus c. Well, I'm going to move all the variables to the right, to the left hand side. And this is our family of trajectories. And if you look at the equation, well, we have x squared plus y squared, but in this case, both denominators are different numbers. That means that indeed we have a family of ellipses, which indeed matches with the picture that we have. All right? So, what's this again? In this case, a family of ellipses. Alright, that's a family of ellipses in this case. Alright, so for the next example, well, I'm not going to make it in 3 minutes.